Okay. So most of you had CSC 200 previously. If you have not, that's fine. Enter at your own risk. Um, so you already have kind of a programming background from a high-level problem-solving perspective. What I'm going to be introducing in here is your first approach at syntax. So this course should be substantially more difficult than that course. So for those of you who found 200 easy, this should be better for you. For those of you who found 200 hard, this should be a nightmare. Somewhere in between, hopefully. Well, no, I kind of prefer the nightmare thing. I like, one of my hobbies is human misery. It's a thing. So, in any case, if you go onto Blackboard and you see the course stuff set up on here, I already have your first assignment up. This one's an easy one. Several of you use Slack from last semester. We're going to be using it again in here. So if you go to cuwcs.slack.com, this is a communication tool we'll be using. If you already have an account, you can just sign in. Otherwise, create an account with your Concordia email, and it won't ask you any questions for approval or anything like that. And then once you get into Slack, for us, you want to go into the CSC250 group here and join that one. So once you're in there, and then I give you some information about something to post inside. Here we have Etma here. He says who he is, where he's from, and you went to Turkey this summer. Like, okay, like vacation or okay. Do anything good? It's probably hot there, wasn't it? Like 150 degrees. I would hope. I would hope it's less than that. All right, but in any case, this will be your proof that you've created your Slack account and posted in here. I would recommend that all of you get if you have a smartphone, get the mobile app for Slack so you can get push notifications and that kind of stuff whenever things get posted. You can turn on and off notifications for different channels. I know some of you were complaining that last semester, like for instance, like just over the summer here, for example, we have a private thing. This was Battle Hack Chicago, for example. So a bunch of the students who went to that hackathon and stuff like that, we have a bunch of communication that we had in here all summer long. So if you were in this group but not interested in Battle Hack Chicago, your phone would have been blowing up with, especially in like the week leading up to the hackathon. So you can turn off notifications based on which things you actually care about. I would probably turn it off in general, as well as any courses you're not in. But for us in here, I would have notifications turned on for 250 in case I post something in here. So fairly often, if I need to make an announcement related to homework or something like that, rather than shoot an email out to the whole class, I'll probably just make an announcement in Slack that, hey, so-and-so just asked a question about the homework assignment. Just to clarify, this is how it works. Okay, so that kind of information will be in Slack. So if you miss it, that's on you. Questions about that? All right, so we'll be using that reasonably heavily. As an aside, this class will have very time-consuming homework assignments. So be prepared for that. It'll start off not being too bad, but it should be fairly consistent the entire semester. It's not so much that the homework is hard, but programming is a difficult skill. And this semester we're going to actually be using real syntax instead of drag and drop stuff and things like that. So you're going to have multiple battles you're going to be fighting. You're going to still be fighting the, hey, I'm learning to be a programmer battle. We'll kind of review some of that stuff from last semester that you forgot over the summer. But we're also going to be learning you'll have to be fighting the Java battle of, did I forget to semicolon? Where do I put the opening and closing curly braces? Syntaxy type stuff that's going to be a little bit of a foreign thing to you at first until you get used to making those mistakes and fixing them. Okay, so early on, even though your programs are going to be relatively small programs, it's going to be one of those things where your program has 6 lines of code in it and you have 50 errors. Because you've done 3 little stupid mistakes that you fix 1 semicolon and everything's all better. Okay, but that debugging skill set is something that you'll have to go through to get better at that stuff. Okay, so be prepared for that. But then as soon as you start getting comfortable and you start making less errors, and I make the homework harder, so you'll still be spending a bunch of hours on the homework. So one thing I encourage you to do, and just so you can see here, some students have done it in the past. This is from CSC250 last semester. There was a study group in there that they would get together. It was about 7 guys. They'd get together and work on their homework. So any point in time, 2 or 3 of them would be meeting, working on their homework together. They'd ask questions in here. They'd ask me questions in here, and they'd post screenshots of their code, like, hey, I'm getting this error, what's up, that kind of stuff. I encourage you to collaborate in here. I'm going to find out on your exams if you're not learning the stuff. Okay, so for those of you who end up being the stronger programmers who take to this stuff very quickly, you're going to become even stronger by teaching the weaker people. Okay, the weaker people are going to end up becoming the stronger people eventually. I mean, so here's a good example. Any of you know Austin Meyer? 1.5 people. Okay, so Austin Meyer used to be one of the sucky people. He wasn't a very good programmer at all. So he learned from some of the stronger people when he was in 250. Well, he led this group in 300. So, and he became one of our team leads at one of the hackathons at our programming competition we went to in Chicago. So there's an example of somebody who started off being weaker but learned from these groups. So take advantage of that. Ask questions of your peers on here. You can also ask public questions in the 250 channel if you'd like. Feel free to do that, and I'll check it. I'll reply. But if you just say, "Hey, I'm stuck in this portion of the homework assignment. Anybody have any hints or anything like that?" Use Slack for that type of stuff. Okay, I'm not going to try to catch you cheating. Okay, it'll be pretty obvious when you get a 3 on your midterm that you're not learning the crap. Okay, questions about that? All right. So that's the Slack side of things. Syllabus is also up here, pretty standard, dealy flippy. All right, so this is the description of the course, whatever, blah, blah, blah. Grading scale, 45% of your grade will be homework, 15% will be pop quizzes. Expect those, I would expect at least 1 quiz a week. Part of that is to make sure that you're doing your homework and kind of learning the stuff. The other part is it's my way of taking attendance. So if you're going to skip class, you might miss a quiz. And remember, that's 15% of your grade. So you can ace the rest of the class and still only get an 85 if your attendance sucks. 20% midterm and final. I have my usual policy. So let's say which benefits a lot of people in the programming classes. Let's say things haven't quite clicked for you by the midterm. You come in and just bomb it. Well, if you do better on the final, I'll replace your midterm grade with your grade from the final. So 10 on the midterm, 90 on the final, you got 2 90s. I won't go the other way. You can't get a 90 on the midterm and a 0 on the final and get 2 90s. All right? So, I want the midterm I don't want the exams to be big stressors. I want the exams to be proof that you've learned what you needed to learn from the class. But I also want you to know that it's reasonable for things to have not clicked by midterm for some of you. Programming is a very frustrating thing. We talked about this more last semester, but I'll reiterate it here. I want you to really treat programming as a sport, okay? And it's going to be even more apparent this semester now that we're actually getting into real syntax. But for those of you who play any sport, basketball, tennis, whatever, you can academically learn how to shoot a jump shot in basketball. But until you've shot 10,000 jump shots, you're not going to be able to just passively do it in a game, okay? Even though you understand how a jump shot works. So, that's something I want you to keep in mind. Programming isn't something you can just crash course on. And, right before the night of the exam, think you're going to crash course and come in and be able to do well in the exam. It's something you need to be spending the time on the homework during the semester. You're going to hate me because you're spending so much time on the homework, but then you're going to look back near the end of the semester, you're going to say, oh, that assignment I spent 7 hours on, I can do in 5 minutes now. It's that different, okay? So it's not that the assignment took 7 hours, it's that it took you 7 hours with your skill set back then. Make sense? All right. So I do accept text messages with like videos of crying. I take that into consideration. I actually appreciate it. But I'll probably laugh, but I do appreciate it. So, and those of you who've had me before know that I'm serious. So, so in any case, questions about the grading scale in the class or any of that stuff? All right. Normal 90, 80, 70 grading scale. Top 2% in each one is the plus, and bottom 2% is the minus. I've been known to curve before, but don't expect it. Um, something that we run into from I think high school these days is this idea that it's like, oh, you paid your tuition, so you should get at least B's, right? Um, that doesn't fly. I would say in general, I'm a pretty easy grader if you put in the effort. So several of you probably got better grades last semester than you thought you probably deserved based on what you submitted. Well, that was because you worked hard in the class, you engaged in the class, and you did whatever. Well, if you just show up, that's not worth a B. That's worth an F. You gotta you gotta put in some effort and do some stuff. So I'm not going to penalize you for good effort, but I am going to penalize you for not doing anything, then coming crying at the end of the semester. I'm not going to have any I'm not going to have a whole lot of sympathy for you. All right, questions about the course, any of that stuff? So you can read through this, whatever. This talks about the crap we'll be talking about and all that jazz. All right, so then let's go ahead and dive in. As you see here, I also have the link for streaming lectures. I record all my lectures, as for those of you who were in my class last year. They're up on YouTube. You can get the link here. So if you're ever looking for a kind of a soothing voice to go to sleep to, or if you want to go back, something I do is when I give you homework assignments, we solve it in class, the next class. So, sometimes it'll be helpful to go back and kind of step through that and say, oh, well, this is where I went south, that kind of stuff. So I encourage you to look at those and also click on all the ads, right? Are there ads in mine? I think I made a nickel last year. It was awesome. Put that in my retirement account. Okay, so let's go ahead and dive in here. All right, so I'm going to review some stuff we talked about last semester. We'll kind of zip through it a little bit so we don't spend a whole lot of time harping, but I assume most of us had a whole bunch of knowledge spill out of our head over summer. Anybody do anything awesome over the summer besides this turkey thing? Well, Turkey is kind of over there-ish. It's Asia, but I mean, what did you do in Europe?
Just wandered around.
Just literally just wandered around. Was like backpacking?
Yeah.
Really? Oh, that's actually kind of cool. I'm interested now. So what did you do?
I went to Spain, Madrid, Pamplona, Barcelona, ran with the Bulls.
Okay.
Went to Berlin, Paris.
This is all on foot.
I mean, we took trains from
Okay, but I mean, did you like camp and stuff? Or you stay in hotels? What'd you do?
hostels.
Hostels? Okay, so you like legitimately like budget pleaser Europe. Well, that's kind of cool. A cool life experience, right? Yeah, see, I'd love to do something like that. My wife won't let me. Says it's too dangerous. She didn't let me go overnight to the Dells this year. She said I was too fat for the water slides. Just mean. Just mean. All right. So how human beings solve problems. All of us should kind of remember this stuff. What are the 3 things human beings use to solve problems? Go ahead.
Solve questions or
Ask questions. So we have memory, ask questions, repetition. All right. So human beings solve problems using these 3 steps. What's the job of a programming language? Tell a computer what to do. And by the way, I'll put these slides up on the on Blackboard as well. That's on iCloud, so I'll put a link up there. So it's tell a computer what to do. Specifically, though, if we take that a step further, the job of a programming language is to leverage tools that humans already use to allow us to communicate with the computer. Okay, and this is kind of where things get a little flip-floppy for programmers, especially now that we're moving away from kind of the visual where we can do a lot of drag and drop and hoping type stuff, and now we're moving into more syntax, scary looking things, I guess, in the big scheme of things. But you know, human beings are so good at solving problems. Okay, we're so smart. We have this perception that computers are complex, that computers are difficult, they're above our heads. Even those of you, I know a lot of people go into computer science because they want to be video game developers. Any of you in here are interested in being a video game developer? Couple people, okay. So the perception is that video games are complex things. You know, how hard must it be to write the latest version of Battlefield or something like that? Well, I'll tell you what, it's far, far, far less complex than what you did just walking to class today. Okay, human beings are so good at solving problems that our weakness is that we find it difficult to articulate how we solve problems. Okay, what we're going to be learning in here, what you're learning as a programmer, is the mentality, the skill set of a teacher. Okay, now some of you might say, okay, I'm a good teacher, I'm not a good teacher, whatever it is. Okay, well, when you're talking to a human being, you're trying to teach human beings, you're having to communicate with a very complex critter. Okay, human beings ask a lot of questions. They don't always follow your instructions. All sorts of things like this. They also can make fun of you, which then adds to like anxiety. Some people are public speakers, some people are not. Whatever it is, computers won't do that. But you're still teaching a computer what to do. The skill set we need to learn as programmers is how to articulate how we solve a problem into little tiny baby steps. Because we need to give those baby steps to the computer one instruction at a time. Okay? Human beings are so good at solving these problems that we no longer have that ability. Well, I say no longer. We don't have the ability to break those things down into small steps. If you were to explain to me how you walk, you would give me the 55,000 foot view of walking. You wouldn't tell me about the little tiny muscles that you have to contract at different points in time so you don't fall over. You wouldn't talk to me about, the constant cadence of questions. Am I going to fall over? Am I going to fall over? Am I going to hit something? Am I going to hit something? All that constant cadence of questions that isn't even worth your time to notice anymore as you walk down the hall. Most of you probably spent your time walking down the hall texting, right? Because walking was too boring. It was too easy. You just texted. I needed something. Okay. Speaking of walking being boring, something I just ordered that's going to be awesome is one of these new hoverboard scooter thingies. You seen those? I'm going to ride that around campus. I'm giving up walking. Take it to the cafeteria. It's going to be awesome. I had to get the one for fat people though. The other ones have like a weight limit of 220 pounds. I weighed 220 in third grade. But yeah, it's called what is it called? Skywalkers. Skywalker's gonna be awesome. Should be in next week sometime, I think. What was I talking about? Oh yeah, the hoverboard thingy. All right, so we'll have to do a demo day so everybody can ride it. Okay, so programming languages. Tell a computer what to do. Leverage the way we already solve problems. That's the key here. Okay. The programming language's job is to meet us halfway, as opposed to us having to go and talk to this alien. We're all used to dealing with humans. We're all used to dealing with solving problems with other people. We're talking English. For those of you who speak, we have a couple of people who speak other language. I'm just making some assumptions, right? What's your second language? Arabic. You guys. Arabic, okay. So when you guys are talking Arabic, and actually, is Arabic, there's just one dialect, or is it like India where there's 4 million languages? Yeah, that's always weird in India, right? Yeah, I have some grad students that are from India, and even towns that are right next to each other may not be able to communicate with each other because they speak a different version of Urdu or something like that. But in any case, when you're communicating with human beings in English, you're using the exact same problem solving as when you're talking to somebody in Arabic. Because who you're talking to is a human being, right? And human beings have an assumption of a skill set that you're having to communicate stuff to. Okay? So the language didn't make a difference. Whether you're speaking English or whether you're speaking Arabic, you're solving the same types of things. Okay? Your thought process is the same. Same thing's true with programming languages. The language doesn't matter. We're going to be using a language in here called Java. Couple of reasons for it. First of all, it's because it's platform independent, so I don't have to worry about whether or not you're a Mac user or a PC user or a Linux user or whatever it is. I don't have to deal with that. Okay, we can all use the same tools. We can all do our homework in our dorm rooms or at home, whatever it is. So it's a very good language for education where, for instance, this semester I'm teaching the 390 course, which is Apple Watch programming. We're writing software for the Apple Watch. Well, you need a Mac for that. So the students who have Macs can do their homework at home. The students who don't are going down to our lab. Brand new iMacs in the lab, by the way. Just put them in over the summer. So even though they look the same, they're brand spanking new. Okay, so in any case, programming language is trying to meet us halfway, more than halfway. Instead of us having to learn how to talk to this alien computer, it's going to give us a means to talk to the computer in a way that we're already kind of used to. Okay, that's the job of our programming language. All right, the next slide, and you guys saw this last semester, is I like to call this one the mapping. Okay, so every single programming language will have facilities for these three things. Memory is variables. Asking questions is something called conditionals, usually if statements. Repetition is loops. 100% of programming languages will have facilities for these three things. 100% of them. Okay? So if you already have the programming skill set, you're already a competent programmer and there's a brand new language you're interested in learning, if you can just sit down and figure out how do I do variables, how do I ask questions, how do I do repetition in that language, you can already solve a large classification of problems using that language. Okay, so now to make our jump. Some of these are things that we dealt with last semester, but now we're going to start fleshing them out with Java-specific things. Okay, so I'm going to start with variables. All right, so variables, what are these guys? These are named containers for storing a value. Okay, variables come in two flavors in Java. Okay, Java is what's known as a strongly typed language. Okay, if you remember from last semester, we had that slide. There are two kinds of programming languages, strongly typed and loosely typed. Strongly typed languages require that we define the kind of value a variable is built to hold. Loosely typed languages do not. So last semester we were working with Blockly a lot, which did not necessarily require us to define the value a variable was associated with, but we had to use certain kinds of values for certain types of things. If we were using a loop to count through things, you had to use numbers, that kind of stuff. Well, Java is a strongly typed language, which means we always have to define the type of value a variable is built to hold. 100% of the time. There's never a situation in Java where you can define a variable without an associated type. All right, real life example of this would be the difference between a strongly typed and a loosely typed language is if you go to Target and buy a Tupperware container and you put a little piece of tape on there and mark it tax documents, put it under the bed, whatever, and that's where you're going to keep your tax documents. Well, later on you decide, okay, well, I'm not going to pay taxes anymore. I'm giving up on that. I wouldn't recommend that, by the way, but maybe you do. So now you're going to store shoes inside of that tax document container. Well, Java wouldn't allow that. Not allowed to store shoes in something that was earmarked for tax documents. Got to go out and get a new container. Okay? Loosely typed languages, like some of our web languages, Python, Ruby, things like that, which we'll kind of incorporate into some of our stuff here, they would allow for that. But for us, want to store shoes, got to go out and get another variable to hold shoes. Okay? So Java is one of these languages. It's very explicit as to the kinds of values our variables are built to hold. Okay? Variables come in two flavors. Okay, we have primitive type variables and we have object type variables in Java. Okay? Primitive type variables, again, we heard this last semester, these are built into the language and are only capable of holding a value. Object type languages may or may not be built in, which implies that we can make our own objects. Okay, may or may not be built in and can hold 0 or more values and potentially 2 more. This would be through functions, methods, etc. Things we dealt with last semester. Okay, so those are our object types. So variables come in 2 flavors. Our built-in primitive types are from a time ago, and we're going to kind of go back, and we have a similar slide to this last year, talking about the lineage of languages. We started with C, but we're going to fill in the blanks a little bit more here with this guy. Okay, we did this last semester, right? Where we had C, C++, those guys. Okay, so we're going to kind of go through this kind of quickly. So if we look at the evolution of our languages and where Java fits in here, we have C, C++, and then Java. Okay, so what we really care about in here for getting us where we're at for the language we're dealing with in here, there's some other languages that come after this, is we really care about the transition from here to here to here. Okay, so we want to review that specific transition. All right, so we're going to look at the evolution of C. Okay, and C I like to look at through that perspective of variables, and this is where we're connecting it to those primitive types. Okay, so C supported variables, so single value with single name. It supported an array. So this is a single name with a collection of like values. And then it supported something called a struct. Okay, struct is a single name with a collection of named values that are not necessarily the same. Okay, so this is what C had within it. All right, just to show you a real quick example of a struct. I know we did this before as well. I might have a struct person, and person might have a string name and an int age. So again, we have a single variable name with a collection of named, so here's name, here's age, variables that are not necessarily of the same type. Okay, so now what I can do is I can go and create a variable of type person. Person p.name is equal to Mike, p.age is equal to 15, something like that. Okay, so that's what structs let us do. All right, and this is what led us in to a necessity to evolve to the next language. So we called C a procedural language. Okay, so we'll call this procedural language or our older kinds of languages. There's nothing wrong with procedural languages. In fact, they're still used today. A lot of video games are still written in C, or aspects of those games are written in C. Okay, but there is a weakness specifically with C, but that weakness was not realized initially. That weakness was realized years later. Okay, as the types of problems we were solving became more and more complex, we started seeing some of the weaknesses in C. We couldn't pull off all the stuff we needed to do in C. We needed something more. But we really liked the things that C did do. Okay, and this is kind of our punchline here, that all of our modern languages, Java included, has its lineage seated in C. That's C programming languages. If we understand where we came from, we can understand where we are now and where we're going. Okay, so we're going to say that C here is procedural. And then when we move to C++, this is our object-oriented. All right. So remind me, what's the difference between a procedural versus object-oriented language? Go ahead.
Isn't this the telephone?
It is the telephone one. What's the difference?
It's, I believe, object-oriented is the wires not showing, and then the procedural is all the, it's more of a mess.
Yeah, all the details, right? So connect the dots here. Job of a programming language, leverage the way human beings already solve problems and let us tell a computer what to do with that in mind. Well, in real life, when we think of a telephone, we think of something that looks like a telephone, not as a pile of wires that just happens to allow you to make phone calls. Okay? The C programming language allowed us to implement things like the pile of wires. Okay. Still worked. We could implement a telephone in C. It would just be a really, really, really ugly, complicated looking telephone. Now, that was fine for a really long time because the types of problems we were solving in the early days of computing were very primitive problems. We didn't really wrap our mind around all the things that we were going to ultimately do with computers until our computers started getting faster and faster and faster, and we started kind of stumbling upon new things we can do with them. Okay? Now we kind of take it for granted, right? Every new thing that comes out, we figure out how we can automate it. And now we're replacing people with robots, and I think we're going to have the whole real-life Terminator thing soon, right? Isn't that right? Skynet and machines taking over and all that. You guys got to watch the news. As Stephen Hawking is warning us about making too many robots because they're going to take over. I can't decide if that would be entertaining or not. Is it entertaining or terrifying?
Probably terrifying.
Huh. Well, I mean, you assume if they're taking over, the programming must be at least decent. I don't really want them to shoot us. They kind of pen us together and we're just inside. We're like, oh my gosh, we got ourselves into this mess. Then you have to do the whole revolution thing and see how you can break out. Man, but those Terminators look mean. Who would make a machine that looked that mean? Like, why did he have to have the teeth? All right, so in any case, the job of our programming language is to leverage the way we already solve problems. C, which was a procedural language, did that job very, very well for a very long time until the problems we were trying to solve started becoming more and more complex, where having the mess of wires became more and more noticeable. When we were solving little tiny problems, having a couple of wires here and there, no big deal, right? If you're building, if you're getting into computer organization, computer architecture stuff, and you're building a little circuit that has like one wire that goes from here to here, it just looks geeky, right? Nothing wrong with that. Nobody's scared of one wire. You start getting 200-300 wires and things are sparking sometimes, and you don't want to see the sparks, even though they sometimes happen. You don't want to see them because that's scary. All of a sudden, we start finding a need for kind of putting it inside of a container because it freaks us out less, and also to protect the wires and that kind of stuff. So as our problems we were solving became more and more complex, we needed a language that kind of helped us with that. Okay, and that's where we evolved to. So this is procedural, shows all the details, object-oriented, hides the details, and only exposes the public interfaces. All right, so our modern languages are all object-oriented. Java is one of those. Okay, so if we're going to kind of create a slide here right at the beginning, that's going to give some definition to Java as we stumble upon it. So Java, we've already decided, is a object-oriented language. It's a strongly typed language. Okay, and now let's remind ourselves the evolution of C++. So keep filling out that chart. So C++ kept the variables, kept the arrays, kept the structs, but added something called a class. What's a class? It's a struct with methods. So now it's no longer a collection of name value pairs. It's also a collection of functions, methods, things that it can do other than just things it can remember. Okay? So all inside of one little case. So we can throw these abilities inside of that, into that class, and then cover it up and only expose the public abilities that we want the rest of the world to have access to. Take the telephone as the example. We have the buttons that we can push. Those are public, right? We will need those exposed. We have the handset. We need those exposed. We don't need the little wires that connect all that stuff to each other exposed because those are behind the scenes type stuff. Make sense? Okay, so a class let us do that. So a lot of people try to make too big of a deal of the difference, the evolution between procedural and object-oriented languages, when the reality is it's a piece of Tupperware. One level of organization. Rather than piling your tax documents on the floor under the bed, we're going to put it inside of a container, label it, and put it under the bed. Okay? Either way, they're under the bed, nobody sees them. All right. So, in any case, Java's one of those. Object-oriented language. Now, we had a slide last year that talked about the difference between low-level, high-level, and machine language, right? Okay, so Java is what's known as a high-level programming language. Well, a high-level language. What does it mean for a language to be a high-level language? As opposed to a low-level language, as opposed to machine language. Go ahead.
One command for, or one word for many commands on a computer.
Okay, so high-level languages, every line of code translates into multiple instructions, multiple magic tricks that the CPU knows how to do, right? Low-level language, it's a one-to-one. So every line of code you write translates into one instruction the CPU knows how to do. And machine languages are zeros and ones. Human beings don't work that well with those. Okay, we screw up too much. Okay, and remember our CPU, we want to think about our CPUs like this dude that has a collection of magic tricks, and each of those magic tricks does a very small little tiny thing. We have to string a whole bunch of magic tricks together in order to solve anything real. Okay, so Java is a high-level language. It's a power tool. We like that, right? We, as human beings, we want to solve problems. We want to talk to this alien that is a computer, but we'd kind of like to do it with the minimal amount of lines possible, right? These are all good things. Human beings like power tools. We like convenience, and we like telling people what to do. We don't like a lot of talkbacks. That's why we like computers. All right. So we're going to say Java is a high-level language. All right. We're going to also say Java is a compiled language. And we had two kinds of programming languages. We had interpreted and we had compiled languages. What's the difference? Go ahead.
Compiled is like ran once and then you can run it again, then run faster, and then, or is that something?
No, keep going. You're in the right ballpark of the lecture. I think what you're really talking about there is the difference between Java and C#. But keep running with it. You might say something funny.
And then the other one, it runs the code each time.
Okay, yeah, so certainly interpreted, that's correct. So interpreted is we're literally walking through our program during runtime, and we read the line of code, we perform the associated magic tricks. We read the line of code, perform the associated magic tricks while the program's running. So we're having to do that translation in real time, okay, which is going to make it slower, right? Just like the example I probably use is something like a president giving a speech or something like that. Okay, if the president's giving a speech in real time and a German news station wants to cover it, well, they're going to have an interpreter that's going to be listening to it in English and then spitting it out in German, and there's going to be a delay, right? Okay, the compiled version of this, of that example, would be that the German news station gets a copy of the speech an hour ahead of time. They can then translate it to German, and then they can deliver it in German in real time to their audience who doesn't understand English, let's say, something like that. Okay, punchline with that is compiled languages typically are fast. Okay, so compiled languages are languages that go through a tool known as a compiler before we run them, and that compiler translates our high-level language, in this case Java, into a low-level language. So kind of it stages it in a low-level language that has a bunch of one-to-one relationships with those magic tricks the CPU knows how to do. So rather than at runtime us having to take this high-level line of code, convert it into a low-level collection of instructions, and then map it to the magic tricks on the CPU, that would be an interpreted language, we can now take our high-level language before runtime, convert it into that list of instructions. This all happens before we run the program. Now when we run the program, we just tick down our list of instructions, mapping it to each magic trick the CPU knows how to do. That's actually called linking, the act of mapping it, and that can actually happen before runtime as well. So you can actually turn it into the actual specific instructions to make it even faster. Okay, so compiled languages are substantially faster than interpreted languages. That doesn't necessarily mean they're better. Okay, why not? Isn't faster always better? Why isn't a compiled language better than an interpreted language? Why wouldn't all languages just be compiled languages? Good. Yeah, whatever. He's answered a bunch. You go. Maybe you'll say something funny.
Maybe because if it's not run in real time, then it can account for changing variables that change each time it's run.
I don't even know what that means.
So like if you like take an interpreted language or an interpreted program, you can change the variables each time and we'll run it with those without any prior variables having to be put in and having to be changed because it runs in real time as it goes.
Okay. I don't know if there's a substantial difference between the two languages with that in mind. But certainly, if I kind of just translate what you're saying a little bit, certainly interpreted languages are probably going to rely on preconceived stuff being stored on the machine before runtime. They're pretty much just going to pick up and go right from where they are, and they can run on any machine as opposed to being reliant on a database or something sitting there. That isn't to say that an interpreted language doesn't use databases. But it really does come down to, at the end of the day, performance. That procedural languages will always be, interpreted languages will always be slower than compiled languages. Is there a scenario where that's preferred? Because the question here is, from a human being perspective, we would typically say that faster is better as long as you're not giving up other things, right? If you can have, when we think about cars, a fast car is better than a slow car, as long as the fast car has as much luggage space and stuff like that as the slow car, right? But typically the trade-off is different, right? The sports cars are really fast but don't have enough room for as many passengers and luggage and stuff like that. Then you have the big SUVs, which don't go as fast but could fit 50 people in them. Okay? So there has to be a similar trade-off when it comes to these interpreted versus compiled languages. Who uses interpreted languages? If you remember this slide from last semester, we had a second collection of stuff over here on this side. We probably had PHP. Then we had probably Ruby. Maybe Python. A couple other ones we might have thrown in there. Let's just stop it at that. So these would all be interpreted languages. And these are all also popular languages, and these are also all web languages. These are languages that are made for the internet, for running websites. So why would they make all of these guys interpreted languages? And these are all native languages. These run natively on CPUs. Go ahead.
Maybe because interpreted languages, let's take the presidential speech. If you're doing it interpreted, it may take longer, but if he says something that's not in the prepared speech, then it's nothing really is missing. But if you're if you have the speech ahead of time, if the president makes a mistake, there's no correction.
Okay, so we can't like real time correct for it. You know, you're basically converting the words that were written ahead of time, right or wrong. These are the words, right? Okay, where you know, in real time when the president's giving that speech, he might zig when he should have zagged or something. He might say, "Well, okay, well this isn't what I want to say," or he might interject some additional thoughts or something like that. Okay, possibly. What I want to think about here is who's the audience of these languages. These native languages, these guys over here, who runs these? Who's the actual audience for these languages? We've talked about it for the last several minutes. The audience for these languages is the CPU, right? Okay, all of these turn into low-level code, which gets mapped to machine language, which runs on the CPU. Who's the audience for these languages over here? Yeah, web browsers. At the end of the day, it's going to be a web browser. All right, so web browsers are not CPUs. They run on CPUs. So we have that, we have that going. But ultimately, these languages are going to be interpreted by the CPU. They go through another filter first, then jump to the CPU because they spit out HTML and JavaScript and whatever. But, allow me to use this as our example because this is a decent way of looking at it. All right, so the web browser doesn't have all these magic tricks that it knows how to do like our CPU. Okay? The web browser has a much, much smaller set of stuff that it's capable of doing web browser-y type of stuff. Those are the types of things it does. CPUs have to be able to do a zillion different things to solve all sorts of generalistic computer problems, right? Not just web browser related stuff. All right, your web browser isn't going to need to, have access to a, there's certainly plenty of things that your web browser isn't going to have to do that your CPU is. All right, fair enough. So these interpreted languages, it doesn't help us to convert them into a low-level language because we're going to have to convert them right back to something else that this guy understands. Okay, at least at some level. All right, but the punchline here is that's one side of it. The other side of it is with interpreted languages typically comes flexibility. Most of our interpreted languages are more flexible languages than our compiled languages. Compiled languages are very, very rigorous. If you get out of line a little bit, they're going to scream at you and things like that, where our interpreted languages still have rules. They still have syntax that you have to follow, but they're far less rigid. They don't make you, for instance, most interpreted languages are also loosely typed languages. So interpreted languages typically do not require that you define the kind of value that's going to be stored in a variable. Compiled languages are typically strongly typed languages. They do require you to define the kind of value that's going to be stored in a variable. Okay? So these things kind of have some caveats. Now, we might say that the people who use these languages are our web developers. Web devs, and I think I probably made a mention last year when I said something like not real programmers. So that's what the dudes over here would say about these people. Okay, web devs, not real programmers. So they need the dumbed down languages that are a little more flexible for their puny minds. They're not capable of doing anymore, right? Okay. So then these guys, these are the native programmers over here. Native devs, and these guys are the real programmers, and they really need more power, even though it might be a little bit more complex and stuff like that. They want the jet engines not the battery-operated scooters that I'm going to be riding up and down the hall. It's going to be awesome. All right. So in any case, we talked about this a little bit last year. Web devs are certainly real programmers. They're more of a hybrid skill set. A lot of times these guys are designers plus programmers. Okay. And another thing you might notice about these languages is these languages are very similar to the types of scripting languages that they're used to dealing with on the design side of things. Okay, so these languages are not better or worse. They're more compatible with the types of tools these folks are already used to dealing with. Okay, these languages are going to be more compatible with the types of tools these folks are used to dealing with. Remember, the job of our programming languages is to leverage the tools human beings already have to allow us to solve problems, allow us to tell a computer what to do. Okay, these languages aren't better or worse than each other. They just lend themselves to different kinds of problems. If you're writing a video game, you're not doing it in an interpreted language. Okay? Interpreted languages, by definition, are slower than compiled languages. Most of the time, this does not make a difference because computers are really, really fast. So if Microsoft Word was written in an interpreted language, probably not the end of the world. Okay? You don't need a killer gaming rig to run Microsoft Word, right? But if you're going to run Battlefield with everything turned all the way up, probably don't want to be running that on the HP budget pleaser from Best Buy. Right? Not going to run real well. All right, so video games are going to be written in our compiled languages because they need to focus on speed. Many, many, many other things can be written in interpreted languages. All right, right tool for the job. One's not necessarily better or worse than the other. Java happens to be a compiled language. But I'm going to say compiled-ish. Okay, Java is a compiled-ish language. Why is that? We talked about this last semester. How's Java a little bit different than our typical compiled language? Because Java is also kind of sort of an interpreted language, right? Go ahead.
Because Java, it's supposed to be platform independent, and so it's initially interpreted, but then they interpret it into the individual lower level machine language for each different OS that it's running for.
Okay.
And from there, it's compiled after that.
Other way around. But you're right. It's so we take Java. So here's our Java source code. Java source code then gets compiled into Java bytecode. Okay, so remember the job of a compiler is converting between a high-level language and a low-level language. So this is high-level Java, this is low-level Java bytecode. Okay, low-level language has a one-to-one relationship with the CPU. In this case, this low-level language has a one-to-one relationship with a software-based CPU known as the Java virtual machine. Okay? So this low-level language goes through this interpreter, the Java virtual machine, which ultimately translates this low-level language into, we'll just use this as the example, this low-level language that is understood by the native CPU. Make sense? Okay, so Java is compiled here before runtime. During runtime, however, our low-level language goes through this CPU written in software, which translates, which interprets that low-level language into the equivalent assembly language for that platform. This might be the Java virtual machine for the PC, the Java virtual machine for the Mac, the Java virtual machine for Linux. Each of those guys knows how to convert Java bytecode into the assembly language for that platform. Make sense? Okay. So this would be an interpretation step. This would be a compiled step. Now the reality is this isn't a fully interpretation step, because we just talked a few minutes ago that fully interpreted languages are taking the high-level language and interpreting it, converting it into the low-level language during real time, during runtime, right? In this case, we're taking a low-level language, converting it to a low-level language. little bit quicker, let's say. Less time is going to be necessary to do that conversion. So Java's definitely fully compiled here, and it's partially interpreted here. Okay? That's why I say that Java is compiled-ish. Okay? We might say this is actually the weakness of Java. So even though Java is fast compared to our interpreted languages, it would be slow compared to most of the other compiled languages. Because at runtime, it still has to go through that little translation step. Okay? What you were referencing is when we talked about last year is that connection between Java and the .NET stuff with C#. Just real quick, that's this guy. So if this is Java, so here we'll say Java, and we'll say C# right here. So Java, C# are both compiled. Java compiles into bytecode. C# compiles into Microsoft Intermediate Language. Same diff. Okay. Java then that bytecode goes to the Java virtual machine. C# goes through the .NET component architecture. The difference is this happens during runtime. This happens prior to runtime. Clearly, those are green and orange, right? That's during, and I think that's the international standard. All right, so this happens prior to runtime and only the very first time you run the application. All right, so it goes through the .NET interpreter, which converts it into native assembly language, and then every single time you run the program from that point forward, it's a native program for that CPU. Okay, whereas Java always does this conversion every single time you run the program. All right, so and Java learned some stuff from this. They introduced something in here called just-in-time compilers, JITs, that try to sort of kind of help a little bit to improve performance, let's say. But again, Java is platform independent, so that's supposed to be really, really good because you can write your applications once and run on any platform. C#, according to Microsoft, is platform independent. It runs on any platform that supports the .NET component architecture, which means it runs on any platform as long as it's Windows. Well, fair enough, but recently, about 8 months ago or so, they open sourced .NET. So we'll probably see them moving .NET over to the Mac side of things, and then you'll be able to, there'll probably be a Macintosh version of Visual Studio, so you'll be able to write .NET applications on Mac, that kind of stuff. Good positive thing for us as developers. C# was already a very popular language. It's not like it's crap. In fact, you might come up here and ask the question is, why was platform independence so important? Let's roll back the clock to the time period when we were dealing with this. Back then, we had, this was probably 1995 or so. Who would care about platform independence back in 1995? Who was being negatively impacted by software that didn't run on both Windows and Mac? Let's keep it that way. Well, who was negatively impacted, really? The Mac people. Everything ran on Windows, right? 99% of software ran on Windows. Still runs on Windows, correct? Well, back then, every now and then, if you were drinking the Apple Kool-Aid, software XYZ wasn't available for the Mac, so you're pissed off. Why can't I run this software on my Mac? It's only available for Windows. Why are we being left out? Why are we being treated as second-class citizens? Blah, blah, blah. So the 5 people that were Mac users back in 1995, they were the ones that were squeaking, okay? And that was the motivation for Java. Proof's in the pudding. At the time, everybody thought the coolest thing in the world was this idea that Java's platform independent. It's going to change it's going to facelift the way software works, blah, 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 things like that. The reality is it didn't. Nobody even cared that it was platform independent after the very beginning. That was just more of a buzzword type thing. Because the only people that were impacted were the 0.01% of the population that was running Linux. And then the 1% of the population that was running Mac. Everybody else was already on Windows. And they already had platform independence because their software ran on the only platform they cared about. No problem, right? Okay. So even though this was cool on paper, the reality is that platform independence for Java wasn't really a thing. Nobody really cared about it. Just like with C#. Last semester we say the joke, well, C#, platform independence. It runs on any platform at all, as long as it supports the .NET component architecture. So it only runs on Windows. Well, anybody complain about programs not being able to, that C# programs don't run on their platform? Oh, most people who are computer users today are Windows users. Okay, so fine. Apple computers are more popular today than they've ever been, but nowhere near the install base that Windows has, right? We're making a move over towards kind of a mobile type of install base. So Microsoft's losing that war. You have what, 1% of society is running Windows Mobile, and 99% are running either Android or iOS. So fine. And now we have a different story, a different war on that. Windows is not losing their dominance on the desktop. Maybe they've dropped to what, 96%? 95%? Come on. We have these nice $3,000 new iMacs down there, and I think they default boot into Windows, right? And they run the Mac OS as well, but Windows is a very, very, very prominent thing in technology. So people don't really care about platform independence is the punchline. And really the only people that were super complaining back then were the gamers, because it was mostly video games that would come out for PC and not out for Mac. Okay, how many of you in here are gamers? You probably see a lot of hands, I would expect. Okay, how many of you are PC gamers specifically? Okay, several of you. Now, if you consider yourself legitimately a PC gamer, you would never buy a Mac. You build a gaming rig, right? Okay. It's not that Macs suck at playing video games, but you have so much more control over your gaming experience if you build your own computer and put the graphics card that you've researched and you want in there and all that stuff, right? And all the games you want to play are at the very least going to be available on PC. How many of you are PC gamers that are just really upset that favorite game of yours is only available on the Mac? Not a one of you. Right? Not a one of you. It's like, oh, that would actually be a really funny thing. They announce some giant game that's coming out and only released on the Mac. That would really hurt their pocket. So, I know, it's funny. I think Mac people think they're way more important than they are. Maybe in like the video industry or something like that. Arts, the Photoshop-y type stuff and video editing stuff. I think Apple kind of has like the market cornered from a software perspective there. But that's like it. I find it very, very fascinating. Okay. Out of curiosity, how many of you have a Macintosh computer in here? 4.5? 3.5? Okay. I probably gave the plug last year, but from a technologist perspective, I know you guys are relatively early on in your computer science careers here. Most of you are sophomores, right? Is that accurate-ish? Sophomore-ish? At some point, if you are in the market for a new computer, I would highly encourage you to get a Mac, not because they're better. Same crap is inside this machine as inside of your PC laptop. The reality is that most people, their argument is the Macs are too expensive. The reality is Macs are cheap when you look at it from the perspective that it's two machines for the price of 1.7. As a technologist, you're going to have to sometimes work in Windows, you're going to have to sometimes work on the Mac side, you're going to have to sometimes work on the Linux side. So now you can have one computer that runs all those different platforms with a Mac. Can't do that on a Windows machine. Outside of using some of the third-party stuff, there's a project on PC called Hackintosh that actually has come quite a ways. It works pretty well that allows you to run the Mac OS on a PC, but a little bit quirky. But from a technologist perspective, you're going to be working with technologies from both sides, right? You cannot do iPhone-y type stuff, Apple Watch-y type stuff, Apple TV type stuff. There's a whole ecosystem where you have the ability to make money and work for companies and stuff like that you can't do on your PCs. So one machine lets you do all the crap you might need to do. Pretty good Pretty good idea for students if you are in the market for a laptop. Get a 13-inch MacBook Pro or something like that. Drop $1,000 on it. Pretty good machine. Dual boot it, get a bigger hard drive on it. Dual boot the thing, Windows and Mac, and you got everything you'll need. If it's grandpa who wants to just check his email, you'd be stupid to get him a Mac. Why spend $2,000 on a machine that you can spend $150 on with a hand-me-down off eBay or something like that? All right. So, in any case, filling out our thing here with Java. So Java's compiled-ish. Fine. So object-oriented, strongly typed, high-level, compiled-ish programming language. That's what Java is. Okay? All right. So let's go down here. And let's start specifically talking about Java variables, specifically primitive types. All right, and we're going to go through this relatively quick because we also looked at this last year, but I never actually connected it to Java. I just introduced primitive types in general. But you'll remember most of these. So we had byte, short, int, long, char, float, double, and Boolean. Remember these guys from last year? Okay. These are all the primitive types that are built into the Java programming language. Okay, if you want to make these the primitive types built into the C programming language, it's that. Want to make these the primitive types built into the C++ programming language, it's that. Want to make these the primitive types that are built into the C# programming language, it's that. All right. So the only thing and it's even funny, why would they just change Booleans? But whatever. In Java, it's Boolean spelled out all lowercase. Okay? All the rest of these things exist in every single one of those languages. Why? Because the parent language there is C. They all came from C. It's not like Java just decided to follow suit. Java's syntax is based on C++, which is based on C, and they're closely based. It's not like it's like took it into consideration. They're the same language, for lack of a better. We're out of here at 11:20 or 25. Okay, well, plenty of time. All right, so byte. These are whole numbers. Short, whole numbers. Int, whole numbers. Long, whole numbers. Char, whole numbers. Why do we need so many different ways of holding whole numbers? Last semester. I heard somebody mumble memory.
They all get bigger, store more space.
Okay, why is that important?
Sometimes the variables that we'll be using are larger than what a byte.
Okay, well, so this guy's an 8-bit number. This guy's a 16-bit, 32, 64. This is actually 16-bit because that holds unsigned numbers. We'll fill in the blank with some of these next class, but just at the high level here. So you said sometimes you need to hold bigger numbers. Okay, fine. Wouldn't it be reasonable for us to say that we can just store everything nowadays in longs, a 64-bit number, and worst that happens, we waste some space? We have a bunch of memory today, right? You get a new computer today, you probably came with 8 gigabytes of RAM. So why did all these things all came from C? Why do they exist?
When the first computers came out, RAM was really expensive.
Yeah, RAM, memory, super expensive back then. Super cheap today, but really expensive back then. I think we did the math last semester, but something along the lines of about $120 or something like that per megabyte. I think was the per megabyte. Remember, there's 1,024 megabytes in 1 gigabyte. So you go to Best Buy today and you buy a 4 gigabyte chip at retail because you don't have the patience to wait for it to ship online. What's a 4 gigabyte chip? $40? Just use that as a rough estimate. So $40 divided by 1,024. Well, $40 gets you 4 gigabytes. So it's really $10 divided by 1,024. So that's less than a penny. Less than a penny per megabyte. compared to $125 or $130 per megabyte in 1996 or 1997. That's major. That's huge, right? So we went from memory being really expensive to memory being super cheap. All right, so we'll pick up from there next time. Remember, to do your homework assignment should only take you about 5 minutes or less. So don't forget to do that. There's nothing you have to put into Blackboard for it. Just do your thing on Slack, and I'll go through the list and give you credit. All right? And I'll see everybody on Thursday.